Okay, we're recording.
That's awesome.
Thank you. It was fun to do, and they'll be using it actually today in their um, seminar. Well, some of them will be anyway.
It was impressive that you used all that to make some with some code.
Well, I'm just getting used to web coding now. I mean, there's a lot to it, and I know a little bit, but
Yeah.
enough to be able to do this. Basically, I used the same coding language that I put your homeworks together with.
Oh, what do you use?
It's called ASP, Actor Server Pages. So I wanted something. I needed something that would be sort of server side because I want students to be able to save their comments and things like that. You can't do that with like JavaScript if you know JavaScript because that's client side. But I was basically just learning as I went along. But it's really thanks to you all that it's working. So I am very grateful.
No problem.
Okay, looks like it is 10 o'clock. So I want to talk about section 2.1, matrix algebra. So how do matrices interact with each other? Let's talk about the easy stuff first. So there are several things you can do with matrices. One is you can do scalar multiplication. So let's say I give you a matrix, 1, 2, 3, 4. And then I say, take that matrix and multiply it by 5. I hope you won't have to think too hard before you guess how this happens, but you just take this 5 and you multiply it by the 1. 5 times 2 is 10. 5 times 3 is 15. 5 times 4 is 20. That's all there is to scalar multiplication. Any questions about that?
Basically distributing.
Yeah, just distribute it over. Just multiply it across every entry in the matrix. Matrix addition. So if I give you a matrix 1, 2, 3, 4, and I ask you to add it to matrix 2, well, 2, -1, 3, 5. If you had to guess how to do this, I'm guessing you would guess correctly. It's going to have 4 entries, just like each of these matrices have 4 entries, 2 rows, 2 columns, 1 plus 2, 2 plus -1, 3 plus 3, oops, 4 plus 5. In other words, the matrix 3, 1, 6, 9. And if you want to jump straight from here to here, that is completely fine with me. Now, when you're adding matrices, it should be clear that the matrices have to have the same size. They have to have the same number of rows and the same number of columns as one another. So note, to be able to add two matrices, they must have the same size. So, for instance, you can't add these two matrices. That just doesn't, you can't. This doesn't make any sense. The first one has 2 rows and 3 columns. The second one has 3 rows and 2 columns. You can't add them. And matrix subtraction works the same way as matrix addition. So, given 2 matrices, of the same size, let's call them A and B, A minus B is just the same as A plus -1 times B, just like it is in, algebra for numbers. A minus B, if they were numbers, is the same as A plus -1 times B. So scalar multiplication, matrix addition, those are easy. I mean, if you had to guess how it worked, that would almost certainly be what you would guess. Matrix multiplication, this is the interesting part. So let's first start off with how this works. So let's say A is an m by n matrix. So m rows, n columns. Remember, we always write the number of rows first and the number of columns second. And let's say B is an n by p matrix. So in other words, B has the same number of rows that A has columns. B has the same number of rows that A has columns. So let's let B, we'll write it out in terms of columns. So its first column, I'm going to call lowercase b sub 1. So that's just the first column. This is a vector, a column vector. And since B has n rows, since capital B has n rows, the vector B1 is going to have n entries. And then here's the second column, B2, which also has n entries. And the third column, B3, also has n entries. And since we have P columns all together here, the last column is going to be B sub P. So here's the first column, here's the second column, third column, fourth column, all the way to the P column. So I haven't actually told you how to multiply these two yet. We define the matrix AB, A times B, to be the M by P matrix, M rows, and P columns. So it has the same number of rows that A has rows, and it has the same number of columns that B has columns, and N doesn't even appear anywhere over here. And this is how you define it. AB equals, its first column is going to be A times B1. You already know how to take a matrix and multiply it by a vector. Its second column will be A times B2. Again, you already know how to take a matrix and multiply it by a vector, and so on, dot, 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 until its last column is A, B, P. So you can see that this has P columns. And each of these things is going to have M rows because A had M rows, and that's what happens when you take a matrix and you multiply it against a vector. So let's do an example. Let's say A is 1, 2, 3, 4, 5, 6. And let's say B equals, so since this has 3 columns, B is going to have 3 rows. Sorry. Yeah, that's what I wanted to say. So let's say B equals 1, 1, 1, 1, 2, -1, -1, 3, 0, 1, 2, 0. So this has 3 columns, and this has 3 rows. And so it is okay to multiply A times B. This has to have the same number of rows that this had columns. So AB, according to what we did up here, is just A times this first vector. So A times that first vector, 1, 2, 0. So we're going to take this matrix and multiply it by that vector. And its second column is going to be A times the second column vector over here, 1, negative 1. Oops. 1. The third column is going to be A times 1, negative 1, 2. And the fourth column is going to be A times 1, 3, 0. So the final matrix is going to have 4 columns. And this is just 4 problems that you know how to do. You know how to take a matrix and multiply it by a vector. So if I take the matrix A, which is 1, 2, 3, 4, 5, 6, and multiply it by that first column, 1, 2, 0, you take out your fingers. 1 times 1 is 1. 2 times 2 is 4. So 1 plus 4 is 5. Plus 0 is just 5. 4 times 1 is 4. Plus 5 times 2. So 4 plus 10 plus 0 is 14. So the first column of the matrix is 5, 14. Then you'd work out the other 3 columns. So let's just do one more column. So 1, 2, 3, 4, 5, 6. What's that second column? 1, negative 1, 1. So 1 times 1 is 1, minus 2 is negative 1, plus 3 is 2. 4 minus 5 is negative 1, plus 6 is 5. 2, 5. And we will have 2 more columns, something that goes here and something that goes here. So this is how you define matrix multiplication in terms of something we already understand, multiplying a matrix by a vector. Let's just see how you're going. Okay, looks like you're mostly finished writing. However, I am going to tell you right now that I never, ever write it out like this. Let me show you what I actually do when I multiply 2 matrices. We're going to get the same answer. And you'll see very shortly that you're doing exactly the same operations. I just never write it out like that. So 1, 2, 3, 4, 5, 6 times 1, 1, 1, 1, 2, negative 1, negative 1, 3, 0, 1, 2, 0. So I know right away I'm going to end up with something which has 2 rows and 4 columns. It's going to have the same number of rows that my first matrix has rows, and it's going to have the same number of columns as my second matrix has columns. And just like when you're taking a matrix and multiplying it by a vector, you need 2 fingers. And just like before, your left index finger goes across and your right index finger goes down. So when I want the first row and the first column of my answer, I go to the first row over here, and the first column over here and do this. 1 times 1 is 1, plus 2 times 2 is, so this is 4, so 1 plus 4 plus 0, 3 times 0 is 0, is 5. Now I want this entry right here, second row, first column. Second row, first column. 4 times 1 is 4, plus 5 times 2 is 10, so 4 plus 10 plus 0, 6 times 0 is 0, is 14. First row, second column. 1 minus 2 plus 3. Second row, second column. 4 minus 5 is minus 1, plus 6 is 5. First row, third column. 1 minus 2 is negative 1, plus 6 is 5. Second row, third column. 4 minus 5 is negative 1, plus 12 is 11. First row, fourth column. I mean, it's tedious, but not difficult. 1 plus 6 is 7, plus 0. Second row, fourth column. 4 plus 3 times 5 is 15, so 4 plus 15 is 19, plus 0. What did I just say, 19? Yeah. And voila. As I said, tedious, but not difficult. Not conceptually difficult. Is that okay? Let's do another multiplication to practice. Let's say A equals 1, 2, 3, 4, 5, 6. And let's say B equals the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. So first of all, is it okay to multiply A times B? Does B have the same number of rows that A has columns? It does, right? A has 3 columns and B has 3 everything. So we can do this. And we know that our answer is going to have 2 rows, same number of rows as A, same number of columns as B. So, whoops. So AB is going to be a 2 by 3 matrix. And have the same size that A has. So take out your fingers and do your thing. So first row, first column, 1 times 1 is 1, plus 0, plus 0. Let's do, I don't know, let's do first row, second column, 0 plus 2 plus 0. First row, third column, 0 plus 0 plus 3. Second row, first column, 4 plus 0 plus 0. Second row, second column, 0 plus 5 plus 0. Second row, third column, 0 plus 0 plus 6. Hey, AB looks like it equals A. So B, this matrix B, is sometimes known as I sub 3, or just I, if the size isn't too important. So the matrix, let me say the n by n matrix with ones down the diagonal and zeros everywhere else is called the n by n identity. And it's denoted I sub n, or sometimes just I, if we don't really care too much what the size is. And I think it's pretty clear to you right now that if I take a matrix and I multiply it by the identity, assuming that this has the same number of columns that this has rows, so this is actually defined, this is just going to be the original matrix A. And if I take a matrix A and I multiply it by the identity on this side, assuming this has the same number of columns that this has rows, so it's defined, this is just going to be the original matrix A. So this identity and this identity might not be the same size if A is not a square matrix, because over here, this has to have, this I has to have the same number of columns. Wait, this has to have the same number of rows that this had columns. And this has to have the same number of columns that this had rows. So these two identities might be the same, different sizes if I'm using the same A there, if A is not a square matrix. If it doesn't have, square matrix means has the same number of rows as columns. You know, when you write it out, it looks like a square. Identities are always squares. So the identity matrix is always a square. N by n, same number of rows as columns. How do you feel about this so far? Is this working out for you? Awesome. So remember, we thought of, so if T going from Rn to Rm is a linear function, we know that there exists a matrix, we say an m by n matrix A, such that T of x equals A times x for the vector x in the domain. So even though a matrix and a function aren't quite the same thing, in my mind, that distinction is kind of blurred. When I see a matrix, I'm thinking, oh, that just stands for a function from a linear function from one dimension space into another dimension space. That's how I think of matrices. I mean, I can write them out as rows and columns of numbers, but I think of this as a function that eats vectors in R3 and gives you back vectors in R2. That's what I think of this. It's not really, I mean, but this defines a function via matrix multiplication. So, if A is an M by N matrix, and B is an N by P matrix. So now, since, well, let me wait till you're done writing. Now, since the second matrix has the same number of rows as A has columns, I can multiply. So AB is defined. You can multiply in that order. Not necessarily in the other order, because M might not be the same as P. But the number of columns of this first matrix is equal to the number of rows of the second matrix. I can multiply this. So we can define T going from Rn to Rm, a linear function, in the usual way. T of some vector, let's see, I'm going to call this U equals A times U. And I can define another vector. I can define another linear function S from Rp to Rm using B. So here, U is in Rn, and here X is in Rp. Wait a second. Did I get that right? Rn. Yeah. Wait a second. Sorry, this should be from Rp to Rn. That's why I was confused. So since I have a linear function over here that goes from Rp to Rn, and another linear function that eats vectors in Rn and spits out vectors in Rm, I can compose T and S. When I say composition here, I mean composition the way you learned about it in pre-calculus or when we reviewed it in a calculus class. It's the same idea, and I'll talk about this again in a second. But I just don't want you to think that there's some sort of new concept going on. It might have been a while since you thought about this. It could be rusty, but this is something that you know well. So I don't have to teach it to you. All I have to do is remind you of it. So we can compose T and S. So T composed with S will eat a vector X. T composed with S is just, we talked about this in calculus, this is just T with S in parentheses. So we have like these big parentheses here, and then you put X in littler parentheses inside. So X is a vector in RP. It's eaten by S. That gives you back a vector in Rn, which is great because T eats vectors in Rn and gives you a vector in Rm. So for those of you that had me for Calculus 1, I told you a story about one of my favorite errands that I ran with my mom when I was a little kid. And we went to buy soda, or where I grew up, it was called Pop, at this bottling factory. And I loved going there. I loved to watch the machines. What would happen is the bottles would come out of the dishwasher and they go onto a conveyor belt, like they come out of the bottle washer, go onto a conveyor belt. And the first stop on the conveyor belt would be this carousel where they got filled with soda. And then they'd come off that carousel and go onto another short conveyor belt, and they'd end up on another conveyor belt, which would cap them. It would cap the bottles. And they'd come off that conveyor belt and go into another machine, which put them in boxes, put the bottles in boxes. So the output of one machine would be the input for the next machine. And that's exactly what's going on here. You have X going into the S machine. And what comes out is something called S of X. And that goes into the T machine. So maybe it's getting filled with soda here. The output of the filling with soda is filled bottles. They're the input for the capping machine. And what comes out is T of S of X. And you can write this using composition notation if you like. Let me go right through this. Let me put it up here. Now, what makes this a little bit more interesting than the example in calculus is in calculus, you have a number go in, and what pops out is a number, and then you put that into the second thing, and then what pops out is a number again. But here, every time you go through, the dimension of the vector you end up with changes. So you start off with X in RP. What comes out is S of X, that's in Rn, and that goes into the T machine, and what pops out is a vector in Rm. Excuse me.
Bless you.
Thank you. This office is so full of chalk dust, it's not even funny. You should see the keyboard for my computer. It's only through the heroic efforts of the building custodian that you can actually see me and I'm not lost in a dust cloud. So this business of multiplying matrices, that's all we're doing. We're composing the functions. So if I take A times B times X, you start off with a vector X in RP. B times X is a vector in Rn. And then A times B times X is a vector in Rm. Yeah, that's what I want to say. So AB defines the function T composed with S. So when you multiply matrices, all you're doing is composing functions. That's all there is to it. I mean, yeah, that's all there is to it. If you understand that, that's great. And furthermore, I sub n defines the identity function on Rn. So if x is a vector in Rn, then the n by n identity matrix times x is just equal to the original vector. It's the vector which does nothing. So if I gave you this horrible big matrix, but it's the identity matrix, so 1, 0, 0, 0, 0, and then 0, 1, 0, 0, zeros all the way down, 1's all the way down the diagonal. Let's say this is a 10 by 10 matrix, and I ask you to multiply it against the vector 1, 2, 3, 4, 8, 9, 7, 2, 8. Anyway, it's just going to be this original vector again. 1, 2, 3, 4, 8, 9, 7, 2, whatever. The identity matrix multiplied by a vector just gives you back the original vector. It's the identity function. It defines the identity function, the function which does nothing. Now, how are we doing? 10 minutes left. That's good. There are a few properties of matrix multiplication that I just want to talk about. A complete list is in the book, but a lot of them you would do automatically anyway. So a few properties of matrix multiplication. Matrix multiplication is associative. You can group things however you want. But matrix multiplication is not commutative. Even if you could do the multiplication in both directions. Multiplication is not commutative. Let's just do an easy example. Let's let A be the matrix 1, 0, 0, 0. And the matrix B will let be 1, 1, 1, 1. So easy matrix multiplication. Now, because this has the same number of columns that this has rows, and this has the same number of rows as this has columns, I can multiply those in either direction. I can multiply AB and I can multiply BA. I would like you to do that. I would like you to take A times B, and then I would, so this is 1, 0, 0, 0 times 1, 1, 1, 1. And I would also like you to compute BA, which is 1, 1, 1, 1, and 1, 0, 0, 0. Take your fingers out. This one's going to be easy. 1 times 1 is 1. 1 times 0 is 0. So that's 1. 1 plus 0. 0 plus 0. 0 plus 0. So A times B is that. And B times A, 1 plus 0. 0 plus 0. 1 plus 0, 0 plus 0. So A times B and B times A are not the same. That looks like an H, but it's supposed to be not equals. Not equals. So matrix multiplication is associative. You can group as you want. So if I have A times B times C, I can do the AB first and then multiply by C, or I can do the BC first and then multiply by A, as long as the order stays the same. Okay. Let me teach you about transpose. T for transpose. You use it like a superscript. This is going to be the easiest thing. The first row becomes the first column. 1, 2, 3 across becomes 1, 2, 3 down. 4, 5, 6 across becomes 4, 5, 6 down. That's all there is to it. You just take the matrix and you sort of flip it along the diagonal, like, and there it is. So a transpose doesn't even have to be the same size as the original, right? This had 2 rows and 3 columns, and that has 3 rows and 2 columns. How do you feel about this? Matrix, yay! So this is basically all of the matrix algebra that we need in the course. That's it. Taking matrices, multiplying by a scalar, taking matrices, adding and subtracting them, taking matrices and multiplying them, to transpose once in a while. Is that good? Awesome. Well, in that case, go enjoy the last 4 minutes of the 15 minutes, and I will see you, well, some of you I'll see in like 14 minutes, and others I will see again on Friday. So take care, everyone.